All right. Good morning, folks. I hope we're having a good Tuesday so far. Let's go ahead and get going. Okay. So today we are talking about circular motion, and we're actually going to start getting into some of the calculations involved with that. So this little clip that we have here, this is just going to show us the relationship between cycles in time. That is frequency. So the amount of cycles that it does in a period of time is frequency. We have period is big T, and that is the amount of time per cycle. And then if we look at the bottom here, frequency is F is 1 over the period. That is on your formula sheet, this one right here. F is equal to 1 divided by T. Or actually, sorry, this one on the right is, but if you manipulate it, it's the same thing. So T is equal to 1 over F. We'll find this one on our formula sheets, okay? But yeah, so the amount of time that it takes for an object to rotate is going to be the period. So the time that it takes for it to complete one whole cycle is the period. And then the frequency is going to be how many cycles per second, okay? And this will probably make a little bit more sense as we get into some of the calculations, all right? This is a good video to just kind of summarize and review some of the things that we've already talked about, and also to introduce some of the topics that we're going to be talking about today. So please take the time to watch this video. I will include the link to that on the Google Classroom. Okay, so we're going to get into some terminology right now. So one cycle is the time it takes for something to make one complete back and forth oscillation. So if I'm talking about my hand, and this is where its point is, this is where it starts. If it goes down, up, and then back to its starting point, that is one cycle. Okay, so if we're doing a circle, if this is the starting point right here, that is one cycle. So boom, boom. That is our cycles right there. Nice formulas, gentlemen. I appreciate that. A revolution is one complete cycle for an object moving in a circular path. So for example, for a planet, if it starts out right here, as it goes around the circle and comes back to the starting point, that is one revolution, okay? Time or period is big T, okay? Make sure you remember that. This is the time required for an object to make one complete cycle. So how long it's going to take that object to start here and return to that point. That is the period of a rotating object. Next and lastly, we have the frequency. This is the numbers of cycles per second, which is measured in hertz. You might also see it in revolutions per minute, which is going to be abbreviated as RPM, okay? We will get into converting RPMs to hertz a little bit later on. I just need to find my mouse again. Where are we? All right, there we go. Okay, period and frequency. Oh, let's talk about, oh, there we go. Okay, period and frequency. So the period T is inversely related to its frequency F. So time is period in seconds, and F is going to be our frequency. This is measured in hertz is the unit, or per second. That's what that means. Seconds minus 1 just means that it's in the denominator. So I'll show you what I mean there. So the frequency of something could be like 0.67 per second, or 0.67 hertz. So that's just saying that it is going to rotate this much of a period per second. So 0.67 per second, or 0.67 hertz. So this T is equal to 1 over F. We'll find that on our formula sheet. Okay, and F is 1 over T. So if you're given something in frequency, I will encourage you to convert it to period right away. It's just going to make our lives a little bit easier when we are solving problems. Okay, so period and frequency are related to one another. Okay, so frequency, the units for frequency is hertz, which is the same as saying how many cycles are occurring per second. It is common to see measurements of frequency in non-metric measurements, such as revolutions per minute, RPM. So when we are given things in RPM, we need to convert them into hertz before using them in questions. So because hertz is cycles per second and revolutions per minute is the amount of cycles per 60 seconds. Remember, there's 60 seconds in 1 minute. If we're going from RPM to hertz, we can just divide the amount of RPM by 60. That will tell us the amount of cycles per second. And if we're given it in hertz, which is cycles per second, and we want to convert it to RPM, we're just going to multiply it by 60. Okay, so pretty easy converting from RPM to hertz. We just need to divide by 60. Okay, so make sure we know how to do that. Okay, here is an example 1. I'm going to leave all the calculations until I'm going to do another video with the calculations. So I'm going to hold off on solving these examples until now, or until then, sorry. So these are some problems that are associated with the frequency and period topic. So again, we're going to solve this in a separate video at the end. Okay, now if we want to measure the speed of an object that is rotating in a circle, we can do this, okay? Now, from the first couple, or the first unit in particular, we use this formula here. Velocity is equal to displacement over time, or speed is equal to distance over time. Okay, we're going to use that same formula to find speed for circular motion, although it's going to be a little bit different, okay? So when dealing with circular motion, the distance the distance the object travels each revolution is equal to the circumference of the circle. Okay, so remember, for circles, that is a perfect circle, okay? So the distance across the whole thing is called the diameter. Outside distance of a circle is the circumference. The inside distance of a circle is called the diameter, and half of the inside distance is the radius. So I lost my cursor again. Oh, okay. So if we look at right here, so the distance on the inside across the circle, that is going to be the diameter, and then just half that. So from the center of the circle to the outside of the circle, that is going to be the radius, and the entire outside of the circle is the circumference. So if we wanted to calculate the circumference of a circle, it is 2 times pi times the radius of a circle. Now, if we substitute this formula into our velocity formula, we can, we will substitute the distance of the circle with the 2 pi r, because in circular motion, the distance is going to be the circumference of the circle. And still, we're going to be dividing by time to find that. Okay. And that, well, we'll get there. Okay. So the last thing we need to fix here is the t at the bottom. So little t is just time, but we are concerned with the period when we are dealing with circular motion. So we're only interested with how much time it takes for the object to go around the circumference once. So we need to find the object's rotational period, not the time. So we can just substitute the period, so big T, for little t there, okay? So this formula here, V is equal to 2 pi r over t. This is on your formula sheet, the last row of the kinematics section, okay? So you don't need to remember that, but just know if we're calculating like the speed of an object experiencing circular motion, this would be the formula we would like to use. So V is velocity or speed in meters per second. Pi is pi, of course. R is the radius, and T is going to be the period in seconds. Perfect. We had a little applause. I like that. Okay, and we're going to manipulate this formula one more time, okay? It's not always needed, but sometimes it's going to make our lives a little bit easier. If we have period t on the bottom, remember the formula for frequency is 1 over t. So if we substitute 1 over t in there, v is equal to 2 pi r over t will become velocity is equal to 2 pi r times the frequency. Now, this formula is not on your formula sheet, so I would be careful with using this. I would recommend kind of being familiar with what is on the formula sheet, what you're going to be able to use on a quiz or a test, and just kind of get comfortable with that. But there is a possible shortcut here, just so you guys know. Okay, again, this is an example, so we're just going to hang off on that until the next video. Okay, so we're going to combine some more formulas here. So we know, so we just talked about velocity is equal to 2 pi r over t, where t is the period, r is the radius of the circle that an object is moving around. And the centripetal acceleration, this is a new one today. Centripetal acceleration, AC, is equal to the velocity squared over r, okay? Again, this is on your formula sheet here, so no need to remember that. Cool, so if we want to combine these two formulas, we have V right here and V up here. So we can just substitute what V is equal to in this particular case and just substitute that right into this V here. So that's all we did. So AC, so going from this formula to here, we have AC is equal to V squared over R. We know V is equal to 2 pi R over T. So we're just going to sub that in. So we have AC centripetal acceleration is equal to 2 pi RT squared, 2 pi R divided by T squared divided by R. Okay. Now, oops, let's go back one. Oh, I need to go ahead. There we go. So then if we simplify, we'll distribute that squared into there. We'll get 4 pi squared R squared over T squared divided by R. This R and that exponent will cancel, and we'll be left with centripetal acceleration is equal to 4 pi squared R over T squared. And this is on your formula sheet as well. Okay, so that is a good formula there. And kind of like we did with the switch with the period and frequency and the velocity formula, we're just going to swap out F squared because we have 1 over, so frequency is 1 over T. If we just square both sides, we'll get F squared is equal to 1 over T squared. So we can substitute that into here, and we will get centripetal acceleration is equal to 4 pi squared times R times frequency squared. Now, just be careful here because this formula, AC centripetal acceleration is equal to 4 pi squared times R times frequency squared, is not on your formula sheet. So just be careful when you're solving that problem. This right here, centripetal acceleration is equal to 4 pi squared R over T squared is on your formula sheet. So I would get familiar with being able to use this formula right here. So again, we will hold up on the examples until the next video. Okay, so we'll talk about centripetal force now. So remember, centripetal acceleration faces towards the inside of this circle. Okay, centripetal acceleration faces towards the inside of the circle. There we go. So if we have an object, ooh, that was really good. Let's try that again. There we go. There's a circle. All right, so remember that the centripetal acceleration faces towards the inside of the circle of, if something's moving in a circular manner, the centripetal acceleration is towards the inside of the circle. Now, according to Newton's second law, when we have an acceleration, we must have a force. In this case, the centripetal acceleration and the centripetal force both point to the inside of the circle. So if we know the centripetal acceleration, using this formula right here, AC, centripetal acceleration, is equal to V squared over R. If we find the centripetal acceleration there, and we know the mass of the object that's rotating, we will be able to calculate centripetal force. Okay, so you guys have the A is equal to F net over M on your formula sheet. A is equal to F net over M. So if you just arrange this formula, which is, this formula is on your formula sheet. If you arrange it, you will get force is equal to mass times acceleration. We've seen this before. Okay, so that's how you're going to find the centripetal force of an object that is rotating in a circular fashion. All right. Any questions so far, fellas? All right. Good. Cool. All right. So we're going to combine some more formulas again. So we can combine centripetal force is equal to mass times centripetal acceleration with either of the centripetal acceleration formulas. So centripetal acceleration is equal to v squared over r. Centripetal acceleration is also equal to 4 pi squared multiplied by the radius over t squared. Okay, so we can substitute that in from this point into this formula here, like we did. So centripetal acceleration is equal to v squared over r, so we just substituted that in there. Centripetal force is then equal to mass times velocity squared over r, which will give us a centripetal force formula of mv squared over r. Now, this is not on your formula sheet, but this is right here. Centripetal acceleration is equal to v squared over r. So if you can just connect these two formulas right here, you should be able to get the centripetal force formula, no problem. Okay. So I just had some notes up here. So these two will be on your formula sheet. These two up here, and these two will not be on your formula sheet. So just make sure you're able to go from these two formulas to sorry, I jumped ahead one. Just make sure you'll be able to go from these two formulas to right here. On this next slide, again, centripetal acceleration is equal to 4 pi squared r over t squared. That is on your formula sheet. And this kind of is, we just talked about that. So make sure you're able to combine these two formulas to get your centripetal force formula, okay? And note, you do not actually have to combine these formulas. If you would prefer to find the centripetal acceleration first using this formula, that's fine. And then you can substitute centripetal acceleration into this formula to find the centripetal force. Whichever works for you. This is just kind of like a shortcut, so you don't have to solve for two problems, okay? And similarly, we can substitute the frequency for period in this formula. So remember, frequency squared is equal to 1 over t squared. So if we substitute that in, we'll get centripetal force is equal to 4 pi squared times the mass times the radius times the frequency squared. Okay, and again, this is not on your formula sheet, so just be careful about that. Okay, this is an example. This is just a video here of an astronaut, or it's actually, he's a reporter, and he is kind of experiencing the centripetal force of essentially a centrifuge used by NASA to kind of prepare astronauts for the large degrees of acceleration that they're going to be experiencing either during takeoff or when they are returning to Earth. Okay, so I will include this link in the video as well. It's just kind of like a good lead in to this problem that we're about to solve in the next video, okay? So again, we will skip this until next video. And that's actually where we're going to stop for today, for the lesson anyways. So these practice problems are not going to be for marks. This is just for you guys to kind of practice what we have been discussing throughout these lessons. Okay, so yeah, so I'm just going to stop this recording now, and then we will continue with the calculations.